Okay, well, good afternoon, everyone. Today, my plan of action is we're going to be talking about the CTAG and manufacturing process of the number 2, the distinguish between the manufacturing processes such as forging, extrusions, castings, forming, and finishing. I'm going to be showing you what we do here at Edison. And depending on the time, I'm going to go ahead and go probably over to speed and feeds and industrial safety. And what I'm planning on doing next Tuesday then is getting into basic machining, showing you some pictures of our lab, some of the projects that we do on the lathe, the mill, and I'll probably end up in basic CNC programming, then also show you some simulation software that we use, but some simulation software that you can actually download free, which we used to use. Okay, so when we talk about castings, all right, we start really getting, this is our chapter 5 and 6 in the textbook. We start talking about sand castings, and again, this is what we do in our lab. And I'm going to be showing you some pictures of some things we do in our lab. I get into the various aspects and the parts of the casting itself. Here we're looking at the cope, the drag. The cope is the top portion of a flask, and then the drag is the bottom portion of a flask. And then we look at the gating system. I talk about the pouring basin, the sprue where the metal goes in, goes through the gating system if you have a gate or a runner. And then we have the riser, and I talk about the purpose of the riser is to escape gases, but we also use it that when we pour, when we see metal coming out of the riser, we believe we have a complete fill. So when starting, this is actually what they'll see. We actually go, and this isn't at Edison, but we take a field trip, and I'm going to end up with that also and tell you about where we go, but they actually get to see a casting process, and the company that we go to literally will wait till we get there, so they'll do a pour so that they can actually see that. The crucible and the flames, the sparks, etc., so on and so forth. So when we look at the casting setup then, there again, you see my riser there, and again, we have the cope, we have the cheek, if we have a middle section in our foundry process, our setup, and again, we have the drag, we have a bottoming board, again, we have the runner, the gate, and then the parting lines, the sprue, and the pouring basin. What I try to share with them is, and you'll see some patterns here after a bit that we use. The students can use their own pattern if they want to pour something. We do pour aluminum. As we're looking at this PowerPoint, I also try to stress that when we put this flask together, we want to make sure we've got the guide pins, that we have it marked so proper alignment that when we take this apart to pull the pattern out, and then we call button it back up, putting a runner, etc., so on and so forth, and button it back up. We want to make sure that we have this thing aligned, because if we don't, we could be 180 degrees off, and next thing you've got a mismatch casting. So when we look at the cope, and again, the drag is shown with a little bit more pictures as far as we do use green sand out here in the lab. Again, we also talk pretty heavy about pattern draft, why we need it, so we can actually pull the casting out of the sand. Talk a little bit about cores and the purpose of the cores. And then this is actually the casting process. I actually have a paper that I pass out that what they need to do in lab, but they'll see their pattern as we come up here, and they put it on the bottoming board, or the splitting board, I'm sorry. And then, actually, no, it's bottoming board, okay? And then what they'll put the cope half on, and we'll ram the sand, as you can see. And this is what it actually looks like, is that when we put the sand in there, we'll put some baby powder in here. And as we put the baby powder, that helps us to release the pattern from the mold. And then we'll start ramming, which we actually have some rammers that literally hit the sand as it comes through. And then as you can see over here is that what we're doing here is we're going to be doing our sprue and our riser, and we actually have a pipe that we end up doing that. We don't do any core prints But again, what I'm looking for is just the basic operation. This is what it's going to look like here when we actually pour it out. And then down in here is what it looks like when we button it up. So again, you'll see that the process. I talk about a comparison of sand molding methods, whether it's green sand, chemically bonded, or shell. When we take our field trip, they actually see all three of these processes, and the company will talk about the advantages, the disadvantages. In the casting processes that I talk about, we stress quite a bit about what's the tolerance of the various dimensional tolerances of the casting processes. I talk about what machining allowances do we allow, pattern costs, what's the lead time, and service finish. You know, because we get to a die casting, it's a lot smoother than, of course, the sand casting. So I get into some of the processes, and every one of these I actually have videos that will show these processes. I just looked on YouTube a little while ago, and there are several YouTube that you can actually get to on the web and show the various processes. This is a die casting, and we talk a little bit about the die cavity coming in and forcing the metal in the molten metal, forcing it up by a plunger up into the cylinder, until the die. It comes around here like this and goes into the process. So as we go down, we actually force that metal in, and then we're bringing it into the opening of the cylinder, and then of course you have a knockout. This is another one that we're just showing a cross section, and again we have the air supply coming in. They're forcing the metal to come in and going into the die head, releasing that. The video that I show, it's a automatic process where they'll shoot what we call shoot the die, wait for a little bit of time for solidification, open it up, punch it out, close it up, and ready for the next shot. So again, we're looking, it's arcade, but again, it shows the process where we have a plunger coming through and pushing the metal into the die itself, showing complete filament, and then opening it up, and then again you can drop this down on the floor and they'll shut it back up and ready for the next die. Just another one, a movable die, and again as you can see how it opens up. Again, you'll see the video. They also have this on YouTube. So it's very, to me, it's simplistic, but it's very precise. So then we look at the investment casting process, and this is the process where we actually have a pattern, a solid pattern, and then we have the gating system in the pattern, and you'll see the gating system here in a few moments on some of the things that we do here at Edison. And as you have the gating system, all right, and then you've got the molding, and again we have a video that actually shows this, and I believe I even have a link to that on tonight so that you'll be able to see that. And then we actually have the pattern removal, and then of course you have the casting as it comes in. So it's almost very similar to the sand casting process. Centrifugal casting, what we end up doing here is you actually pour molten metal into a round cylinder, and this is rotating all the time. All right, so as this rotates, it forces the metal up against the outside wall, and as that moves outside, it forces the impurities to go actually inward. And with this, here's where we make a lot of brass bushings, pipe, etc., so on and so forth. Again, we have a video that shows that. So this is always turning when this comes in. Very good micro finish on this, and very good holding tolerances. So when we talk about comparison of the sand casting processes, we talk about the sand casting itself, what's the advantages. And again, it does provide a great deal of flexibility. And you have few limitations as far as size and shape. And I use the scenario, the company I used to work for, I used to have to outsource some castings, very large castings. I actually had a company that build their flask on a cement floor, and this thing was like about 12 feet by 6 feet, the flask, and they would use that to go ahead and hold the mold, all right, and then pour the metal into the mold. You do have cement molding, and again, it's a variation of sand casting that does use a special sand-cement mixture that is molded into the sand. And then as the molds are dried, they are very high strength, and then, but it's more costly than the green sand because of the process and the other limitation. You really have to use it pretty quick because the material will rapidly become hard. Shell molding, again, it's a special form of sand casting that uses a conventional but finer sand coated with thermosets or heat hardening resins, mainly used for cast iron castings. And again, it's more accurate versus the green sand, and because of that, to a certain point, is very expensive. Then we have the plastic, I should say mold casting, similar to the sand casting, except the pattern is used only once, then destroyed. So it provides a good micro finish up to about 125 micro. You could get a 50 to 60, can be produced, mainly used for non-ferrous metals, rubber, and plastic. Investment casting is known as a lost wax or precision process. Here you get very close tolerances, 3 to 5 thousandths on complex parts. You have the higher cost in this process because of the die design. You're generally limited to about a 35-pound limitation, and you have a long lead time. And generally the lead time is because you've got to manufacture and produce the die itself. The permanent mold casting is where you have 2 or more parts that you use repeatedly for production. You get very good grain structure, better grain structure, but again, you have the higher initial cost because of the mold itself. And then we talked a little bit already about the die casting. Permanent mold, except, the molten metal is forced into the cavity about 1,000 to 3,000 psi. Extremely close tolerances are held, and again, you have a very high cost factor. So it really depends on what you're going to be doing with your part, and is it going to, what kind of post work are you going to have to do after you cast the part. Talked quite a little bit in pattern making, and generally pattern are made out of wood. You could make them out of metal or plastic, and then you want something to retain its shape as you force the sand around the material itself. And we explain about the shrinkage allowances that we allow on a pattern. So in other words, once it solidifies, like Manel, brass, magnesium, and bronze and nickel is going to shrink about 3/16 of an inch. Cast iron about 1/8 of an inch. Malleable iron. Steel is about 1/4 inch. Zinc and lead about 5/16, and tin is 1/2 inch. So a pattern maker needs to know the shrinkage allowances. And then you've also got allowances you need to watch out for because your degree of finish desired. What are the different types of metals, the shape, and the size? And generally speaking, a pattern draft is about 3 degrees for small patterns and 1/2 to 1 degree for thicker patterns. In the lab, they're required to pour 1 casting, and it's up to them if they use one of the patterns that we have out in the lab, and I believe I have about 14 patterns out there. I've had students that will make their own pattern, and again, you're going to see an example of that here in a few moments. So what happens if I really have a complex part? Well, then we can actually make one out of styrofoam pattern. And the advantage of that is that, for instance, you've got your styrofoam, and all we do is pack the sand around it. Now, what he did is actually put the pouring basin, the sprue, the runner attached with the casting itself. So what happens here, and again, he's got his riser coming up right here. When you pour the metal, then it will actually burn the styrofoam, and again, it's a lot of flame, a lot of smoke. But as it starts to solidify, or not solidify, but it's melting the styrofoam, and then it will solidify. You really don't get a very good finish, and because of the porosity of the styrofoam itself. Sometimes that doesn't matter. But again, if you get a pretty good piece of styrofoam, you can go to Hobby Lobby. There's other areas. We have Joann Fabrics just right down the road where they sell styrofoam. And generally what I end up doing, I'm sure that every one of us has bought something and you get styrofoam in it, whether it's a computer, et cetera, so on and so forth. I usually just bring that in and we can use that later for a pattern. So talking about a little bit of loose pattern here, and I actually show this. We're making a gib plate, if you will. And how do we end up doing that? And what we're showing is that we have the loose pieces here. Okay, so when we come down, all right, so that we can pull this out, and then we can just move these pieces out here to the right, to the left, take them up, and then you can see how we can actually pour the metal and achieve the lips that we're asking to produce. And I do actually demonstrate this also. I've had students use this, and then just share with you, because we'll be talking a little bit about CNC programming, but they'll go ahead and pour this, and then later they'll finish the top of it, and then in CNC they'll actually put their initials on top of this for a desk plate. And I've had several students do that. All right, so pattern making, again, these allowance for finish, generally about a 1/8 of an inch for ferrous metals, 1/16 for non-ferrous, and 3/4 inch for large castings. I have various pictures that I can show them of castings weighing 6,000 up to 12,000 pounds. The company I used to work for, we used to do that type of work as far as hydraulic cylinders. And then you need to watch out for sharp corners. They are very hard to produce, and if you can, you want to avoid those. I've had people try to do their initials, for instance, and if you get an A, it's very hard to get that sharp corner in the A unless you're doing a styrofoam pattern. And again, sharp corners are also easily destroyed by the movement of the molten metal. And then we get into the pattern types. We have the flat back. Generally, that's what we'll end up doing, and probably 75% of the castings I pour out here is flat back. And then we have split, and I'll show you an example of that here in a moment. And we've already saw the one slide of the multi-piece, and then, of course, you have the cord pattern. So comparison of the processes then. When I look at the sand, I look at the permanent mold, I look at the investment. This is just really to supplement what I've already talked about, but I want them to see the differences in tolerances, the differences in dimensional tolerance, the size range, and what type of metals each one that you can actually produce as the result of going through the process. And then a plastic mold. Okay, and again, what it's for, up to 500 square inches. And again, we can see the tolerance for that. And plaster mold is for aluminum, zinc, brass, or copper. And then type this up just real quick, but we're looking at a sand casting, and again, the various micro finishes to the left, as we're looking right here. Permanent mold, the investment, the plaster mold, and the die casting. And again, we're looking right here where we can achieve a 32 to a 90 micro. And look at the tolerance. So again, if you've got a part that you're making and you really don't want to do any machining afterwards, and it will fit into the size range, that's the way to go. Sand casting, I talked about, is the fastest process from the drawing board to a casting. And it doesn't take very long to do that. Out in industry, it will take you about a 6-week lead time if you do not have your pattern. All right, foundry terms. The bellows is just an air device that we use to blow the sand off of the pattern, and then I'll blow it from the cavity. Okay, so we don't want loose sand in there. We don't want loose sand in the runners, etc. The binder, and again, it's a bond that we'll use in the foundry sand, such as cereal, pitch, or resin oil. And again, it's just to help us bind it. We talked a little bit about a bleeder, and we'll see this sometimes when they pour the castings. It's a defect where the casting lacks completeness due to the molten metal draining or leaking out. Some part of the mold cavity after pouring has stopped, and generally that will be leaking in the split line. And if we don't button that up or get it tight enough, I've actually seen that. I actually had one casting one time. I had a lady make a dog dish for St. Bernard. She made it out of styrofoam. And what I didn't realize is that when we poured the metal into it, we had so much metal, it actually started making the coat to rise. And then, of course, we saw that metal coming out to the side. We were lucky because we had enough metal that we did get the dog dish. And now she has the only St. Bernard in Ohio that doesn't have teeth. She wanted the dog dish because she never could find a heavy enough dog dish for the dog not carrying it off. Talking about, again, the bosses, and again, a cross-section of the casting, and we'll see a picture of that. We've already talked about the various processes, the die casting, etc. Chaplets or metal supports or spacers used in the mold or parts of the mold to help support the mold in position during the casting process. And I actually have some out there that I get from the foundry, and some of them looks like big railroad spikes just to help hold the mold itself. We already talked about the cheek, that's a centerpiece. Again, the choke is a restriction in the gating system that will impede the metal from going in, so it doesn't really force going into the cavity. A cold shot is a small globular or metal embedded in but not entirely fused into the casting. I got a couple of examples of that. Actually, it's almost just picture, let's say, if we have a ball bearing into the molten metal and it's solidified before the other metal and it didn't provide a coalescence. We already talked about the cope, the core box, the flask, etc., so on and so forth. I have about 4 crucibles out there, and that's a ceramic pot that holds the metal itself. And again, talked about the drag, the gate, the runner. Okay, strike off is removing the SX sand from the core box of the flask. We go through that process. Various impurities, things that you really potentially don't want it in the metal. Again, the ladle. And this run was when the casting is not fully formed, resulting from the metal poured so cold that it's solidified before filling the mold completely. And generally how we notice that is probably what happens is they don't have the runner wide enough or deep enough. So when they pour the casting itself, it starts to solidify and we do not see metal coming up through the riser. And when we have that, we know we've got a misrun. And what I'll end up doing is that we'll break off what we have and I'll have the student just report again. And again, what I'm looking for is they do pour a casting that's satisfactory. And if we mess up, we don't have the screw right, we don't have the riser right, they'll generally have an opportunity to go ahead and try the process again. All right, so again, when should we use the casting processes? And it talks about design and manufacturing engineers must decide when it's advantageous to use the casting process, or in essence, really talk about a fabrication. And as you're looking at, if you got parts that's more complex, you have internal cavities, various parts, you have quite about inaccessible areas for machining, for instance, and you like to have those cavities, then it's wise to go with the casting process. With this, I actually, and again, as you're looking at that, I also talk about the cost comparison. If I would get a quote for a casting versus a quote for a fabrication, and with that, in other words, I have experience with this, but with that, I would say, okay, it's going to cost me so much for the casting, but then I've got the machining to do, and sometimes with the machining, you need to allow extra stock for the dross. In other words, dross is metal impurities that will go to the top of the casting, and sometimes they'll cut that off, but you still have some extra machining to do. Of course, in fabrication, you still have some machining, but not quite as vast as far as the fabrication unless you have internal cavities. So I talk about, again, the lead time, the cost, fabrication, the lead time, the cost, if you have post-heating or stress relieving, et cetera, so on and so forth. So they get a comparison of really when it's advantageous to use either one or the other processes. It also talks about out here at the bottom that it's not advantageous to use the casting process if you can stamp it out on a punch press, deep draw, and again, we'll see a little bit of pictures of that here after a bit. Extrusions or cold heading, or if you have highly reactive metals. So this is actually a reject. This is a RAM that the company I used to work for, and I think you'll see a date on here in a moment, 1999. That's actually when I left the company and came full-time teaching. And what happened, this is a hydraulic ram that goes into hydraulic compression press. So if you think in the old days, I don't know if you see it that much anymore, but you used to go to a filling station, they'd raise your car up, well, they have a ram underneath that. And that's exactly the same process here. And what happened, this operator is running the lathe. As a matter of fact, when I was started at this company, I was actually running this lathe and doing these parts. And he noticed that, first of all, that when he indicated this thing in, or he used a four-jaw chuck and a file just to make sure we're somewhat alignment, and he started turning it, it was out of balance. And that should have told us one thing, that we had a core shift. And I used this purposely to show that. But when he started machining, and then we could see that we're breaking out through the side. So approximately how much? Well, we're looking at approximately 3 inches of wall thickness there. And again, that's a hook scale. And then we're looking about 3 inches going the other way. So what we're looking at is the inside the core of this part. And again, this is what it looks like. All right, so casting comes in, that's what it looks like. And again, you can see the OD here, and he was starting to do the machining, and it started to break loose. So what's it look like on the inside? There you can see that. We have this Basin here, all right, and we actually put a center drill so we can have support and use our tailstock. They check up on this area here. So you got your tailstock coming in here, and you check up here, end up doing your machining. All right, but you can see now going through here how we talk about a core shift. And what we're talking about, if you look at the wall thickness from here to here versus the other side, it's quite a bit of difference there. And I think at this time it was almost like 2 inches. And there's the date, 10/6/1999. And this is the company that I worked for, it was French Oil. So I use this, and again, to show them sometimes on core shift, and I think I showed you that in ultrasonics, that I can actually detect that if we have a core shift or if we actually have a problem with that. Okay, here's the introduction to the sand casting process. And I think I'm just going to start showing you just a little bit of it.
Hi guys, it's Scott here, and in today's video we're going to introduce you to a typical sand casting process. So where does sand casting fit within the scope of all the different manufacturing processes available to us? Firstly, we have the forming methods, and within these forming methods we have both casting and reforming. Casting is a process where we take something that is liquid, sometimes a metal, sometimes a plastic, and then we pour it into a mold and then let it set so that it hardens, and then we take out the part, which we can then do further processing on and machining on to bring up to the final desired standard. So sand casting is one of the most common forms of that casting process. There's also things like shell molding, die casting, investment casting, and quite commonly with plastics, injection molding. So sand casting is the focus of today's video. Within these forming methods, we also have some reforming options, such as forging, and then we get into the machining methods, which we're going to take a look at in future videos, and then joining methods, some of them permanent and some of them semi-permanent or temporary. So today's focus is sand casting, so let's look at a typical sand casting process. Sand casting is the most straightforward way to make metal objects with complex internal cavities in high volumes and medium quantities of objects with complex external profiles. So if we look at this picture on the left here, this is actually an exhaust manifold cast out of iron that you would typically find on a lot of your production cars. And so the hot exhaust gases exit out of the head of the engine through these ports and are collected together and go down and flow on into the exhaust system of your car and your muffler and your catalytic converter. And this geometry has quite a complex shape, and it's got a lot of internal cavities here for the exhaust gases to flow through, and it also gets quite hot, so it needs to be, the material we choose has to be resistant to those high temperatures, and there's also an exhaust system hanging off this, and so it has to be reasonably structural. So in this kind of circumstance, cast iron is a very good option for these types of parts, and we can make them relatively cheaply and in high volume. This is all cast in one piece, and then we perform some machining operations to flatten some of these surfaces so that they can bolt up and seal nicely against the head of the car and also against the exhaust manifold. On the right-hand side here, we have an example of a cast engine cylinder block. So this is something that you might typically find in a motorcycle, and you can see that it has a lot of complex fins on the outside, probably because this one looks as though it's air-cooled, so it doesn't have water jackets and cooling water flowing around the engine. The heat is actually dissipated from this engine by air cooling from these fins. And so this has quite a complex external profile, and this would take a little bit more time and effort to set up for this casting, and so we can't do it quite as easily as the exhaust manifold, but it's still possible to manufacture medium quantities of parts, complex parts like this, using the sand casting method. And if you have a look at this, this is actually cast from aluminium. You can tell by the colour of it, it's a lot lighter than the cast iron example over there. Like the exhaust manifold, this engine block would be cast in one piece, and then there's going to be some very highly precise machining operations which are performed on the balls, these cylinder balls here, to bring them up to the correct tolerance for the pistons to work within, and then it's also got holes drilled and probably tapped to take studs which would bolt down the head of the engine. So these are a couple of typical examples of parts that are commonly manufactured using the casting process. We're going to use the following diagrams to talk you through a typical sand casting process. So the first step is for us to develop what we call a pattern. And a pattern is basically a reproduction of the part that we want to actually manufacture with a few small changes. So this is a wheel that we're making here, which is quite solid, and we can see that there's a bit of a boss on this wheel here. And we've also got something on the tip there called a claw print, and we'll talk about that in a second. So these patterns can be made a variety of ways. Commonly, they're made from wood because wood's nice and easy and quick to work, and it's reasonably durable. If we wanted to make a lot of these parts, then we might make our pattern from something a little bit more wear resistant, such as aluminium or steel. And in this case, due to the casting process and design that we've selected, this pattern for this wheel that we want to make has actually been split down the middle. So there's actually two pieces, and that's going to enable us to build the sand around of our pattern so that we can then pour the metal in and form the shape, and also have a little bit of a runoff here for excess material, excess metal to go into here to make sure that our part is completely full and we don't get any air trapped in there. So in this particular process, we're starting with a half pattern, which is this one here. So the pattern splits in half, and we're going to place that on a horizontal moulding board, which you can see here. And so we'll put this pattern down onto the moulding board, and then we place what we call the drag. So the drag is this component here, and it also has this lip which goes around the side there, as you can tell from the cross-hatching. So if we put that on there.
Okay, again, this is going to follow the process that we've already explained to them, but they can actually see the process. And as I'm looking at this also, we're showing a core, and then we're showing a core print. So when the molten metal will go around that, then you have an ID going through, in essence, where the shaft would go through. And I thought it was very interesting because this sand casting one, and if you go to YouTube, you can actually, he talks about the other processes It's very informative, and I really appreciate having an opportunity to actually use this in my lecture. So I'm going to close this tab. Okay. So when we look at the other one is the most common casting processes. Okay, we'll just watch a little bit of this one.
Sand mold casting, also called sand casting, is the most common casting process. It is applicable to a great variety of metals, and there is essentially no limit to the size of casting that can be made. Castings made in sand molds are not very precise, but production cost is generally lowest. Although the molds are expendable, the sand can usually be reconditioned for reuse. Sand molds, made in halves, are built by tightly packing the sand around the pattern in a flask. The upper mold half is called the cope, and the lower half, the drag. The mold includes one or more risers, venting provisions, and a system for transferring the molten metal to the mold cavity. This system includes a pouring basin, sprue, runner system, and one or more gates. Once the sand has been compacted, the pattern and mold half are separated, and any loose sand is blown away. Cores, if required, are inserted into the mold. Once they are set, the mold is closed by aligning the cope and drag. The mold is then transferred to the pouring station. In casting, metal flows from the pouring basin through the sprue, runners, and gates to the mold cavity. Vent holes formed in the cope and drag, and often in the cores, permit trapped gases to escape. After filling the mold, the metal enters the riser or risers, which serve as reservoirs of excess metal to compensate for metal shrinkage during solidification. Once cooled, the casting is removed
you
from the
saw
mold,
this man here,
and the metal in the runners and risers separated from the casting for remelting. The mold is then transferred to the pouring
but you saw in there that where the metal was coming out through the riser. That's what we hope to see when we pour out here in the lab. All right, so it's very informative as far as another YouTube video. All right, this is out here in our lab. This is the furnace that I use. And then we also have a boxcar furnace. This is the furnace here my son will actually come and get. Of course, he has to borrow my truck. He'll take some of the flask, and I think I have about 8 flasks. The bottom or the mold boards, bottoming board, etc., so on and so forth. This is my sand that we actually have, and this is a machine that will actually break up some of the sand. We keep using the sand. This is a mauler. All right, we keep using the sand. And I think I've replaced this sand. I've been here now 16 years, and I've replaced it 2 times. After so many times that it loses its complexity to stay together, and it really doesn't cost very much. I actually have several foundries here around this area that I can get some materials from. There's a riddle that you use across the top of it, and again, you see the various flasks. All right. So again, this is the flask, the cope, okay, and the drag, and there's a pattern, actually a casting there, and again, I'm going to show that to you here in a moment. Heat the metal up, okay, and again, it gets very hot. I teach safety. They do have to wear the safety equipment. They wear a shield. They wear a coat. They wear the gloves, and they also wear leggings. And again, I have this is what we use here to put the crucible in. So we just set it up on top, reach in there, get it out, and bring it over there on the board. Okay. There's a pattern or a casting that they actually poured. What you don't quite see here is you've got the pouring basin, all right here. And again, you've got the sprue. And as you see how it fell, and I believe the riser was right here, and it cut off or it broke off. I think this one here, you can see it coming out. So again, you can see it, and this is what it actually looks like. I had quite a few people make the bird. And these are just some other patterns. I have quite a few people that like the horseshoe, the dog, praying hands. I have a fish. Again, these are flat back. So in other words, when you turn it over or you just pull it out, you don't have to worry about alignment or anything like that. Just got to make sure you have your riser and your sprue where it needs to be. And what I'll end up doing, I want you to picture this being in the bottom half. And as I look at it, before they call we button it up and they put the sprue in the riser, I want to see the runner and et cetera, so on and so forth, and it looks like we've got it steep enough. We may have to have 2 runners and then 2 runners going to the riser, 2 runners leaving from the sprue, just because of getting enough metal into the cavity itself. It wouldn't take very much metal in this one. There are times when I will put more than one pattern in the flask itself. So sometimes the students will work together and they'll just put runners across each pattern. All right, this is interesting. This is styrofoam. Okay, this was a styrofoam. A kid wanted to make a skull, and as we look at it, okay, let me get rid of it here. We had some issues with it. And if you know, this wasn't designed to be this way. This side should have looked like this side, and it didn't, but you can see the teeth, et cetera, so on and so forth. And he did pour this, and I asked him if I could have it, because he actually made another one, and we actually changed the runner around a little bit, and the sprue, and the riser, and we actually came up with a very good casting. As I'm thinking about this, I actually had another student that had a Mustang, and he made a Cobra snakehead out of styrofoam, and he bought the pretty expensive styrofoam that was really smooth. And the only thing he had to do was drill and tap, so it would go on his gear shift in his Mustang, and he actually made a Cobra knob, if you will, for his Mustang, and it really looked good. I tried to keep it, and he wouldn't let me do that. All right, but he really did a good job with that. With that, we have a 2-piece pattern here, and this is a candlestick. So we have this opportunity to have several of these. I think we can actually pour about 4 of these in the flask. We're looking at 2 pieces, and this is what it actually looks like. So this would be in one half, this would be the other half. So this is where I'm talking about, is that when you look at the drag and you look at the cope, all right, you want to make sure that when you bring this down, that it's actually where it needs to be in alignment with your flask. So we use chalk to make sure that we're in proper alignment. I think I have a poor casting out there where this is actually what we call, it's not matched up very much. He's got about like a 1/4 inch on this side and then missing a 1/4 inch, so it's stepped. What I like about this candle is after we pour it, and generally they'll pour it in pairs, then when we go to the machining processes, they'll go ahead and face it off, and they'll go ahead and drill for their candlestick. So it's something that they can have and take away. Okay. Any questions on the casting process?
Very informative, Steve.
Good. Like I said, my son borrows the equipment, and he teaches at Greenville High School engineering, and they actually just pour it right on the floor. They put sand on top of the floor and the flask on top of the sand. And they'll generally use my patterns, and again, they'll take my furnace there. I like my gas furnace because I can do quite a bit of material in that. When you take the box furnace, it's an electric furnace, you can only pour about half as much as what I can pour. So he's really limited on the size. But again, what he's looking for, and I appreciate this, is that they get to see the casting process. And of course, he's got to do it when I'm not using it.
Sure.
Okay, metal forming. Again, another section in the CTAG. Quite a few videos on that. We talk about roll forming. And again, it's a continuous process for forming metal from strip, cold stock into shapes or uniform cross-section, and the material is fed into successive pair of rolls. And what's interesting about what I'm showing you here, and again, you can have a pre-cut or a post-cut method, I take for sure 2 field trips. And one of the field trips that we go to is Jackson Tube, which is probably about 2.5 miles from Edison. And what they end up doing is, I'm sure you've seen these semis going down the road, these trailers that's got big coils of steel on them. Well, they get these coils of steel in and they slit them to maybe like 2 inches wide, and they feed it through a machine, and then as they go through the machine, you'll see some pictures here in a moment of progressive dies or rolls, and then they will form them, for instance, like a desk leg or a piece of pipe, etc., so on and so forth. And the company works 24 hours a day, 7 days a week. They literally run those rolls all the time, those machines. And what they end up doing is they do not form them. I want you to think of a steering wheel. And as you go in, they've got various finished products that people use their tubing. The company may bend the tubing. And again, we'll see a little bit how that's done here in a moment. But they'll bend the tubing, and one example that they have is a steering wheel for a car. And I thought that was pretty interesting. But again, all they do is cut the lengths. Maybe they're like 26 feet of length, et cetera, so on and so forth. They band them, and then a company will come and get those. So it's pretty interesting when we take that field trip. So, and again, any material known today can withstand bending as desired radius can be rolled. And the material can be ferrous or non-ferrous, cold rolled or hot rolled, polished, pre-painted, or plated. And the thickness can go from 0.5 up to 3/4 of an inch, with widths about 1/8 up to 72 inches or more can be used. And the length of the finished part is limited only by the length that can be conveniently handled after it leaves the forming machine or what you can actually put on a trailer. All right. This just shows you various things, materials that can be formed, what can be done. It talks about multiple sections can be formed from a single strip or several strips fed simultaneously to produce the one composite section. And the only absolute requirement is that the material, whatever the type, the coating thickness or width, can be capable of being formed. Sometimes it talks about here certain titanium alloys have poor forming characteristics at room temperature, therefore it's got to be heated and then formed especially in a rolled forming machine. When I talked a little bit about Jackson Tube, they also when they form this, they actually have a welder that will weld the seam. So it's pretty interesting that they get to see that also. Several types of rolling machines. Roll formers, and again, you have the spindle support, you have a station configuration, and then we talk a little bit about the drive systems. Spindle support, and again, we have some videos that that they get to see this. And again, generally talking about 2 types. You have inboard or outboard machines. And the inboard machines have a spindle shaft supporting one end, which is about an inch and a half diameter and up to 4 inches in length. The outboard machines have housings supporting on both ends of the spindle shafts. And again, this is what we're showing. And again, we have a video showing these cross sections of outboard roll stand with square gearing. And you can see how showing the roll spindles and the micrometer screws. This is an old type machine, but again, you have the micrometer screws up here to adjust for various sizes. And again, we look at a side-by-side machine. The machine is designed multiple profile tooling and provides flexibility of having more than one set of roll tooling mounted on a spindle shaft at the same time. And again, this machine is limited to 2 sets of rolls on this one at a given time, but you can actually have up to 3 or 4 sets of rolls. This is side-by-side configuration. And double high machines. So in other words, it's doing several processes at once as the metal goes through. And it talks about this type of machine is usually for the metal building industry for forming building panels up to 60 inches wide. Nice video on this also on YouTube. Rapid machine, and again, it talks about reassembling the single-duty conventional configurations, which has housing and spindle shafts and one particular set of rolling tooling mounted on it. So it's a removable raft. Okay, going back to this again, one other thing that I show them is when you're looking at progressive rolling dies, the company that we go and that we see, Jackson Tube, I want you to picture those dies in different sections. So it's almost like something like this, but they go in at 90 degrees. And if you have a section, for instance, you may have a roll that's starting to crack, etc. It's making some noise, or it's indenting the material the way it's not supposed to be, something got into it. They'll shut the machine down. So again, when they shut the machine down, they are losing money. When they shut that machine down, there's actually a clock on top of the machine that will start, so that's their downtime. And they have a goal at a certain time to have that machine back up. And generally what happens is they'll actually have a replacement section to go right back in there. So they'll pull it out, put it back in. It's almost like NASCAR. They'll put it back in and get it going again. All right, and it's pretty interesting. Again, we talk about cost of downtime there a little bit. Get a little bit in metal spinning. And again, we'll see some videos on this also, but it talks about the deformation process that we use to make discs, bowls, etc., cones, tubes. I believe one of the videos that I show, they're making bombshells that goes in front or nose for airplanes, etc. Various type shapes in metal spinning. And again, it talks about it's economical. It's a good method of producing these parts. Especially if cost stamping or deep drawing dies would not be substantial. We can talk a little bit about the parts ranging from 1/4 inch up to 26 feet in diameter. That's been spun for metals up to 3 inches or more thickness. I'm thinking, wow, 3 inches or more, that's a pretty good machine. You got to have quite a bit of tons on that. And we talk about manual hand spinning, and you'll see the video on that here in a few moments. I'll show you a little bit of that one. Power spinning, shear forming, and tube spinning. Again, we're looking at some of the processes, the power, the manual, the shear, and again, the tube. We have videos, and again, YouTube has these, so it's pretty informative when we look at these various processes. I used to have some time that we actually showed this out there on the machine, but because we've actually limited our processes class to 16 weeks, and that's got to include the welding and the foundry now. And I used to have 16 weeks of just nothing but machining and plastics. So, of course, by Ohio, the standards, they're trying to get all associate degrees to not be hardly any more than 60 credit hours. So this is a 4 credit hour class, both of them. So I had to combine them, and what I've ended up doing is getting the high points, so the students still get a survey of the process. Here again, we're showing the hand manual, whether it's underarm or scissors type tooling, how we end up doing this, the spinning itself. Shear spinning, conical type shape, coming from a blank. Tube spinning, and again, there's a video there as far as basic metal spinning. I'm going to show you just a little bit of that. It's old, but it still shows the students what's going on.
A base plate is used as a guide to start half straight and remove after a few threads are formed. The finish I'm using is hot. The wood for this mandrel is
I don't know what's happening here, but again, you'll see it.
spinning. The paper is turned, sanded, and coated with wax. The wax allows for easier removal of the finished piece.
Let's try that again.
A mandrel is drilled 7/8 inch with a 1-inch top relief so it fits the threads of my wood. You know, it's almost too pretty to be used. The pieces are first cut 4 inches and then turned to make 4-inch square pieces. Two and a half inches to 10 inches in diameter. This circle is 3.5 inches in diameter. For larger quantities, a punch is much faster. This punch was made many years ago for making plastic lenses, but it also works great for aluminum. It sure comes in handy to have a metal shop to support my other hobbies. Here are several tools made in my shop for metal spinning. A tool rest, this combination tool, and a Scotch-Brite pad. The tool rest has a stop collar for height and a flap milled into it so it can't rotate. A method for centering the aluminum disc is to slightly release pressure on the tailstock while carefully pressing the wood support into the disc while it's spinning, and then tighten the tailstock, pressing on the support blank to hold the disc. Applying the lubricant. And now to start forming the aluminum disc over the mandrel. Notice the fluid is working from center to the edge while applying both downward and side pressure. The reason these tools are so long is so my body weight applies the pressure. The disc stretches and can get out of round. This trim tool brings the disc back to round. With the feeding tool, the edge is rolled over to give a nice finished appearance. Scotch-Brite is used for a nice satin finish. And it's complete.
Okay.
Thanks for watching.
So again, it's something that they can actually see how it's done, and there are videos on YouTube that have very large machines for the metal spinning. Talking about bending and straightening, and again, bending's producing the shapes by stressing metal beyond its yield strength. but not past its ultimate tensile strength. We've talked already about this in our materials class, or materials section, if you will. And then the forces applied during bending or opposite directions, such as cutting of sheet metal and bending the forces. So as we look at it, we talk about sheet and plate bending. And again, it's the process complex that's involving a number of technical factors. In other words, you have your workpiece material, your material flow, your tooling design, what's required to form the bend, and the type of equipment used. And again, we have videos to show that. You have various type press brakes. And again, the opposite is pneumatic press brakes, bending press brakes, manual brakes. So talking about bending terms, allowing for bending allowance, allowing for a dimensional amount added to the part through the elongation during the bending process. And again, just allowing for these allowances. Sometimes what you end up doing is cutting that, what you have left over. Various types of bending, straight bending, flange bending, contour bending, what it looks like. Again, straight bending, very simplistic. Flange bending, a little more difficult. Contour bending. Stretch bending. And then failure modes, you know, why we have failure, where we want to see it, cracks, etc., so on and so forth, degrees, shrink, failure modes. Good video on this also. And we're talking a little bit about straightening then, whether it's cold or hot metal forming processes that they have residual stresses sometimes, whether it's plate, or it's definitely after a fabrication that you may want to straighten the part itself. We'll talk about actually how we end up doing that. Straightening rods, or shabs or tubes. Straightening flat rectangular or irregular shaped parts where you have a bow or camber. I actually talked a little bit about welding also, that if we know we're going to get a bow, we'll put a pre-camber in there, so when we weld it, it's going to be a lot straighter. So what's the principles of straightening? And again, I think because of time restraint, but we have the limitations here of what we need to watch out for. And this link here will show you various straightening presses used in industry. Shearing. How we cut metal, various type shears. And again, the shearing process. Another good video on this one also. And the various types of shears, the manual, mechanical, hydraulic, or pneumatic. Different designs. A lot of companies have what we call the iron workers. That's that one you just saw. That video I just, that link that I just showed you shows several of these different types of shears. Okay, that takes care of that as far as that CTAG. And I think with the remaining time, what I want to show you now is I'm going to get a little bit in speeds and feeds, because I do want to get into machining more next week, and I want to get into basic CNC programming that I can share with you and some of the software. So we already talked about metrology here, and now we're going to talk about a little bit about the turning processes, milling processes, and then I'll talk about the research that we end up doing. So you've already witnessed this, but the RPM equals 4 CS over D, revolutions, diameter, cutting speed, and then the time calculation that we'll end up doing, and the machine routing. And I shared a little bit of this with you already, but they'll actually have a routing. I may give them a print, and I will ask them, okay, I want a routing on it, so you need to know your processes, your routing number, what you're actually doing, and if you have any locating surfaces. The company I used to work for, I actually have some parts that scrap, and I've got the routing and I've got the print so that I can show them that also. Okay, recommended cutting speeds and feeds. There's a lot of charts out there today for various materials, low carbon steel, high carbon steel, etc., aluminum alloys, copper alloys. So that's where we're going to get our cutting speeds for our formulas. Some more for selection of speeds and feeds. Face milling, plane milling, form milling, sawing, carbide face milling. So it's very useful chart to show them the various applications that you'll be using the various cutting speeds. And again, I think I've already showed you this, but I have them do a quote for a high speed or carbide and give me a quote, and I get quite a bit of range with that. Okay, in the lecture, we also talk a little bit about drilling and reaming, surface feet per minute. And again, the different materials for drilling, reaming, counterbores, various steels, steel 4340, 1018, wood, plastic. And again, there's our formula, very similar to what I've used. And then we'll come in and show them an example as far as cutting a high-speed drill in aluminum. So what I'll end up doing is I'll cover this up. You'll see this in a moment, but I'll cover this up, and they'll have to figure it up and see if they can come up with the right RPM. And here's another one that I would give them, stainless steel. So they have to look on the chart, look at the cutting speed, the tool itself, and then what's the surface speed. Drill cycle feeds, how it's calculated as far as the formulas. They talk about different drill diameters here. Counterbore feed, reamer feed, inches per minute. Or I'm sorry, inches per revolution, not minute, but inches per revolution. And again, I show them the chart, and here's an example. This is inches per minute there. And again, they got to fill with the solution, try to come up with it. And on exam, they're allowed to have the chart and they're allowed to have the formula. So they got to come up with the solution. And usually it's a multiple choice answer. And there's one for tapping. Okay, cutting speeds as far as contour pocket machining surfaces, feet per minute. And again, you look at the material. High speed versus carbide. Show them an example. Chip load. Different size, 1/8 inch mill versus 1/8 1 inch. Various steels. And again, another example. Talks a little bit again, reduced speeds when setup lacks rigidity or you want a better surface finish. And this is a website, and again, this is the link up here. This is a website that you can actually have. They have various charts, formulas for drilling, whether inch or metric. And they have, I think, about like 5 or 6 of these various charts you can go to. Unfortunately, you got to stay on the web to get it, so it will calculate it. You can reset it. It's very useful, and it is bitchy. So this is like page 1 of 3. I just gave this to you for an example. Very useful. Show them cutting speeds, etc., so on and so forth. All right, and again, milling machine cutting selection speeds as far as the video. Talks about high-speed machining, etc., and I'll just show you a little bit of this one. It's available.
So there's all kinds of different cutters to choose from, and the thing to always keep in mind is that you want to use the largest diameter cutter that you can that will produce the correct geometry in here. So, for example, if we use a really large diameter cutter like this isn't going to work because, I don't know if you can see that, the cutter diameter is actually bigger than the diameter, than the radius, you know, that's at the edge of the pocket here. So if we tried to cut that with this cutter, you'd end up with too big of a radius there. And as it turns out, okay, so now we know to machine this pocket feature, we're going to speed steel tool here, and we consult the chart. This is for high-speed steel in non-ferrous materials, so aluminum. And down here it says aluminum alloys, 6061. And then for high-speed steel, it says 450 to 650 SFM. That's surface feet per minute. This is a pretty horrible set of units here, but I've noticed even like shops that deal in metric units still use SFM, surface feet per minute, to describe cutting parameters. In any case, what that means is that between 450 and 650 is a good range for high-speed steel cutters, for that moving edge is going through the aluminum at about 5, like this, on the edge of a piece of material. If the cutter is spinning clockwise when viewed from the top.
Okay, this is actually, if you notice, a 28-minute video. Of course, we're not going to be able to see the whole thing. But he goes through the process using his formula and how he came up with his depth of cut, etc. So it's very informative. It is a nice little video to see. Again, this is right out of YouTube. Okay. Talk every bit of this, and I want to finish up today, talk a little bit about safety. And whether I'm teaching welding, foundry processes, machining, lathes, etc., so on and so forth, you've got to hit the safety. And I want to share with you some of the things that I end up talking about. So look at manufacturing safety. We look at the OSHA safety checklist. And there's a checklist. I actually have about 5 of these different type checklists that I will show them. And I'm going to show you in a few moments of some of the materials that I actually use. When we talk about material hazards, I'm going to actually show you a little bit more on machine guarding. But you got a safety checklist. With that, what's the safeguards of important safety? And again, when he talks about, remember the shop is a place to work, no horseplay. I stress quite a bit about no horseplay. And I talk about the buddy system. One of the things that I definitely watch out for here in our lab, sometimes students will ask to come out in the lab to finish their lathe project, milling project, or CNC. They've got to have someone with them. It's a buddy system. If someone gets hurt, no one's around, first of all, they could actually be severely hurt or even actually lose their life. I used the illustration. I had a part that we sent up to Amish country up north, and thinking, is that Perrysburg? Up somewhere up in that area, but and Guy was machining on a Saturday morning, and he literally severed his arm off. And it was on our part that he did that, and he about lost his life. He actually used a sock to stop the bleeding, and then he called 911. When they came, he was already blacked out, but I went and seen him in the hospital. So things happen. I don't want it to happen here, and we definitely use the buddy system. Talk about dressing safety, and again, your sleeves rolled up, no long hair. It's going to be tied up if it's a ponytail, especially the lady. No jewelry, and again, rings or watches. Definitely safety glasses or goggles, and if they have glasses, they don't want to wear the goggles themselves. I do have side shields that they have to put on, and it's a must. Talk a little bit about hand tools. I'm going to show you here in a few moments where I actually have PowerPoints for all this stuff. How do we use the tools correctly? This is interesting. Again, I have a PowerPoint presentation for that also. I'm sure we've all used various things when we weren't supposed to, like using a screwdriver for a chisel or a pry bar. And again, using portable electric tools correctly. Observing all the safety rules when running the machines. And again, you have access to this. And of course, being a good housekeeper, one of my pet peeves is I walk out in the shop, and I used to have a night instructor, and sometimes they would leave and nothing was cleaned up. That's a no-no. I don't have to worry about now because lately I've been teaching both of the classes. So, all right, and again, first aid. All right, so in so doing then, go to machine safeguarding. And what I want to show you is from the National Safety Council, you can actually have access to this. And I want to go to another place here in a moment. And when you look at industrial safety, this is what you get. So you get safety management, communication, health and training, employee involvement, safety and health inspections. We actually end up doing an inspection out in our lab. And with that, one of the things that they'll watch out for is, again, you don't want that too much distance between the grinding wheel and your tool post. Talk a little bit about accident investigation and industrial hygiene. Don't really get too much in ergonomics. I actually teach a safety class, environmental health and safety, where we end up using that. What are some issues? But I want to show you the safeguarding. The objectives and what a machine safeguard is. When? What does OSHA require? And we have videos also that shows the safeguarding requirements. But I've also found some checklists online that I actually pass out also. Supervisors' roles, responsibilities. Every one of these safety videos, you're going to see that. What are their responsibilities? Or maybe our responsibilities. Principles. Systematic approach to safeguarding. You identify the hazards, assess the risks, find solutions, enforce the safeguard use, and then, of course, supervise. Again, this actually just breaks it through one of those sections that we just talked about in that PowerPoint. And again, as I said, we have various support videos for this. And you can get this through the National Safety Council. So very interesting. And again, we talk about fire safety, electrical safety. The hand tools and portable power equipment will stress the proper use, that when and where you should be using the proper hand tool. With that, this is an unsafe practice. This is really one of my pet peeves. If you look at that, what do you see wrong?
Brush on top?
You got the check in the check. Everybody see that?
Yeah.
All right. Actually, what happened here is we have a capstone project, and the capstone students ran the machine that night, and they left that. I came in the next day. There's two problems I have here. Not cleaned up, and they left the check and the check key. What I've done since then, I don't know if you know they're available. Maybe you already have them, but you can actually buy check keys now. It's got a spring on them where you cannot leave it in the check. And we've got those now. So it's not going to happen. But prior to that, again, there it is again. That's the lathe. We actually have four of these lathes, and I got a larger lathe. And I'm going to share some information of some projects we do Tuesday as far as the lathe and the milling, etc., and the basic CNC. But I've got ouch here. And why do I have ouch? Look at that. A kid came to me, and he was bleeding, and he says, Mr. Sykes, I did something you told us not to do. And he left the check, the key in the chuck, turned the machine on, and it hit him right there. And I'm going to tell you, we are fortunate. If that could have been lower, it could have got his eye, or it could have even been worse than that. So I've had 2 accidents, and that's one of them. And I've been teaching here since part-time 81, full-time since 1999. And knock on wood, I don't want any more, but this is one that really scared me. I mean, he was really bleeding, and I'm thinking, oh, man. But that's all it was right there. So, but we were very fortunate. And, of course, I did have him, we did take him to the emergency room because I didn't know if he had a concussion or whatever. But that was it.
Sure.
So we were very fortunate. And I got his permission to go ahead and use this. All right. He says, no, I don't want anybody else to do that. So, like I said, I felt, when I saw it, I thought, oh, man, we're really in trouble. I was going to have to call the ambulance. I looked at it, and I said, we're still going to take you to the emergency room. And it was just fortunate enough he did have a bruise here, but that's all it was. Yeah. Okay? All right, that's it. What I want to do, you notice I have my CNC lab. And let me go ahead and just real quick, I want to show you a auto edit NC. And again, I'm doing a little bit of myself, but I want to show you this is something you can download free. And I'm going to go ahead and I think I can do this. I'm going to open up a program and show you how it works. Okay, you have to have the program in Notepad. And again, I'm going to share this with you next week. I'm going to show you some very simplistic programming that we end up using. So, and I just did that. I can't believe I just did that. Let's do it again. Okay. Make sure I don't hit that one. Well, it was there. I just covered it up. Okay. So we come here, and I'm going to hit simulate. Going to open it up. And I'm going to change my scale down here to 0.5 because right now it's at 1. All right. I'm going to buffer. Then I'm going to bring it down so I can see the red dot. I think you can see it right there. And then I'm going to hit start. Okay, very simplistic. But again, it's a program that you can download in the simulation module. And I have students download this. Some of them will download these on their personal computers. So it's very simplistic, but again, it's showing us the path. And I don't know if you noticed or not, but when this actually started going through, you could see the tool going up and going down. All right, so it's, like I said, it's very, very nice to use. And then I'm going to show you real quick the simulation software package that we bought, but it's pretty expensive. This is called Predator CNC. And I'm going to get, I think I can open up the same job, that initials. I don't want that. Let's see, where did I do with it? I don't think that's it right there. Yeah, CNC Lab, that's what I want to open up. Okay, these are various, I'm going to show you these, some of these next week. But if I go to the initials, I hit initials and say open. All right, and I'll say okay, that gives you an opportunity. This is what you set up. And again, I'm just briefly going to show it to you, but I can go to File, Job Properties, and this is where I set the machine up, I set the stock size up, and I set my tools up in my program. And I'll guarantee you, if you're wrong, it's going to let you know it will not run. Okay, I'm not going to change anything. All right, so I'm going to go ahead and run it so you can see it. Okay, this is one of the requirements they have to do. This is a 4x8 piece of plastic. With this, I have a 10 license for this in our computer room, and they come in and I show them. I'm going to show you the very basic one we do first, but I show them how to set it up. I'll close the job and I'm going to open up another one. I'm going to show you the very first program we end up doing. Okay, this is the first one that they actually have to program. Very simplistic. That's it. So what am I looking for? You have your proper G codes, your home position, your point of origin, 0, 0, and then actually milling this out. So I'm going to, Tuesday, I'm going to show you some of the basic manual lathe things that we do, some of the lectures that I do, the milling, and then I'm going to finish up with the CNC. I'm going to show you a little bit more complex parts that they're doing. And again, this software package here, the initial package is $14,000. And you pay so much for a license, and there's a maintenance fee every year. I'm thinking like $200 a seat. But I like it. I've got a Cadillac here, and I can turn on the air conditioning, and that's it. I can actually set this up to actually look like a full-fledged machine, and you can have the parts inside of it. I can put clamps on it. I can put a vise on it, etc. So right now, as I'm getting used to it, we're just doing the basic CNC programming on it. You do have milling, and you do have lathes. And next week, we're actually going to start some lathe work on it. So this is the first year that I've actually used this software package. Prior to that, I used that free software package.
Now, Steve, I know there's a lot of programs now that'll take 3D models and you can have it generate CNC code.
Yes, you can.
right? And does this package do that?
Yes, it does.
Okay.
Yes.
Okay.
Yeah. Yeah. We looked at Edge Cam.
Okay.
Okay, you've heard of that. And I looked at Predator, but I felt, and I tried Edge Cam. I actually went down to Dayton, a distributor there, and we spent a day working with it. And then I found this here, and I called the company, and they sent me and actually, you can go to Predator software and download a temporary license just to see some of it, some of the examples and whatever. I just felt overall this was more user-friendly than what I need for. And what happens is I'm showing them this, but I actually have a CNC class. I actually have a 16-week class, and later on I'm going to show you some more of the advanced things that we do. They end up doing in my manual machine class, they'll do this, and they'll do their initials, and I actually will go out on a machine and run it. And so they have their initials on a piece of plastic.
Yeah.
Okay?
Certainly.
Yeah. The requirement for the CNC class is they've got to take survey of manufacturing processes first.
Mm-hmm.
Okay?
Okay.
I like what I've used. I mean, it's taken me a while to get used to it. I actually have a student. Matter of fact, he's in there right now. I should take a video of him. He's doing the next assignment. I mean, he's actually going for a job interview Tuesday to do this for industry. And I'm going to tell you, he has picked this up. I'm really proud of him. So
when they're motivated, when they want to do it, they're so motivated.
Oh yeah.
Yeah.
Yeah. Okay. So again, that's covering a lot of the CTAG, and I just want to Tuesday. I just want to go over. We'll have a brief review, but I really want to hit the machining because I think that's a strength of this CTAG also. And I'm going to show you some examples of the parts that we make. Some of the lectures that I do, threading, turning tapers, how do we cut tapers on end lathe, drilling and tapping. We actually chase threads out on the lathe. And again, I'll show you that lecture. And the machine tool tips, the videos that I shared with you already, has really got some good videos for that lecture to support. And then I want to get into the milling, and I'm going to come back to the CNC and just show you a little bit more of that. And then I'm going to share with you where we go on our field trip. Okay, so any questions for tonight?
None here. Thank you so much.
Well, again, I hope it's been informative, and you all have a nice weekend, and I guess we'll talk to you Tuesday.